So next we have Steve Hoover. So good morning, Steve.
Good morning.
Yeah. So we were all waiting for you. Thanks for joining. It's
Thanks for waiting.
yeah.
It's early here.
Yeah. It's I think it's 3 a.m. right? 3 a.m. in the morning.
Yeah, it's 4 a.m.
4 a.m. Okay. That's really very nice of you to join this conference at such a time. So really happy to you.
That's an honor.
Yeah. So I've been working with Steve for past 1 year, and I think we have developed we have went ahead and built an online webinar on transitional verilog, and he'll be talking more about the upgrades and findings about TL Verilog. Steve Hoover is the founder of Redwood EDA. He holds a BS in electrical engineering from Rensselaer Polytechnic Institute and an MS in computer science from the University of Illinois. He has designed numerous components for high-performance server CPUs and network architectures for DEC, Compaq, and Intel. Students will learn transitional Verilog modeling techniques to generate Verilog models in half the time using Makerchip.com free online EDA. So you might want to go through this site because I have gone through it, and the GUI is it's pretty amazing. A new open source RISC-V CPU development effort will be introduced that showcases flexible IP design practices. So we have looked into so many backend things. Now it's time to move into more of a front end, and I would like to invite Steve to present an introduction to transitional level Verilog. So Steve, I'll just open up your presentation and I'll share it, and I'll give you the control.
Very good. I can share from here too if you like.
I have to actually make the host arrangements. I think it is easy. I'll show you. It's pretty easy from here, I think.
Okay, as long as the animations come through.
It should come through, yeah.
Yep. All right.
Are you able to see the?
Yep.
Yeah, I'll give you the control. 1 second. Yeah, just move the mouse and you should get the control.
All right. Okay, good. So thanks, Kunal, and hi, everyone. I want to first congratulate you on sticking through to the final stretch. And I think it's a great honor for all of us to be part of the first ever VSD Open. Kunal and Anaga are really leading the charge for changes in the industry. I expect following their lead, online conferences will become increasingly popular.
Yeah.
I also believe open source hardware is poised to have a huge impact on this industry, and I'll be discussing that briefly with you. As the founder of Redwood EDA, as Kunal said, I'm focused on front-end design tools and methodology. I'm very actively supporting this emerging language standard called transaction-level Verilog that Kunal mentioned, or TL Verilog. And that's the focus of our two front-end talks today. Kunal and I crossed paths about a year ago when we did our webinar. This was back in February, and we introduced folks to transaction-level Verilog. Kunal was very excited at the time about the impact that transaction-level Verilog could have on the open source hardware community, and so he asked me if I could encourage submissions where TL Verilog is applied to RISC-V. And actually, when he asked me at first, I said no. I said, Kunal, I'd love to get students working with this technology, but barely anyone knows about it yet. We'll never get students submitting papers in just a few months. So it turns out there's been a great deal of interest from academia, word spreading fast, and I was even able to get some sponsorship from Google through a program called Google Summer of Code for a couple of students to work on transaction-level Verilog projects. Both students did some really exciting work, and both submitted papers to VSD Open, and I was happy to see that the reviewers were as excited about their work as I was. So before they present, since most people are new to transaction-level Verilog, I asked Kunal if I could provide everyone with a bit of context about transaction-level Verilog so our two presenters can jump right into their work. Let's see how I do the slides here. Maybe I don't have control, Kunal? Oh, there we go. Okay.
Yeah.
So before I jump right into transaction-level Verilog, there's some really exciting things happening with open source hardware right now, or at least there will be very shortly, and I want to talk about some of those trends. And then I'll talk more specifically about transaction-level Verilog and set up for Akash and Ahmed to present. So there's been a lot of interest in open source hardware for many years. The goal, of course, to follow in the footsteps of open source software, which obviously has been very impactful on the software community. And we're making some progress with open source hardware, but it really hasn't launched the way open source software has. So what's keeping us back? Well, there are three main things, and each of these in isolation is enough to pretty much put on the brakes. Access to tools. So EDA tools are traditionally very big, very complicated. They're driven by large EDA corporations, and they're very, very expensive, completely out of reach. Access to hardware. So unlike software, where you can just make your open source software available, people can download it and generally run it without too much difficulty on their own platforms. Hardware is a different beast. You can download somebody's hardware model, but to actually run that model, you need compatible hardware to run it on. Thinking about ASICs obviously is completely out of reach in an open source community. FPGAs are a much better option. But even with FPGAs, a user has to acquire the FPGA, configure the FPGA, get your design compiled and running on your platform, which requires a lot of platform expertise. You have to interface with that platform to talk with the particular design you want to implement. It's a lot of time, money, sophistication, and without that, without the user base in the open source community for the open source contributions you make, there's not that community, community fueling itself. And the third is just the complexity and the scale of hardware. Obviously, if you want to actually produce a chip, you're looking at very significant development effort. I come from a world of design teams that are on the order of 500 people working on a single next generation product for 5 years or so. This is obviously not the scale of open source development. A single chip is billions of transistors. That's a lot for open source community to manage. So obviously you want an ecosystem that builds on itself, an IP ecosystem where open source contributors are contributing smaller IP blocks and others are integrating those IP blocks together, and that's what's happened in the world of hardware over the past several years. But there's still some very significant technical challenges with the ability to provide IP that's generic enough for others to utilize that IP in various contexts at various clock speeds and various technologies. So the IP ecosystem is important. It's evolving. It's not really there yet. So we're still dealing with significant complexity that's getting in the way of making any tangible progress. Fortunately, all three of these very significant barriers are essentially simultaneously breaking down today. So this is a very exciting time to be part of this community. Access to tools, we've seen, and this is kind of why we're all here today, complete open source tool stacks used to design real FPGAs, full chip models. It's very exciting. Access to hardware. The single answer here that's going to break down the challenge of easy, inexpensive, lower expertise access to hardware are cloud FPGAs. All right, so with an ecosystem that contains cloud FPGAs, now an IP developer can develop their IP for a particular FPGA platform in the cloud, and they can make that hardware model accessible to anyone along with the hardware that runs it. So users can now download that design, push buttons, and get that design running on their own in the cloud on the same hardware that it was used for development. So you've broken down the barriers of the expense, the time to acquire the platform, the effort to configure the platform, because now you're running on the same platform that was used for development. The cloud FPGAs are not where we would want them to be yet. They're still very clunky. They're still very difficult to use. They're still relatively expensive. Of course, they use a rental model, so there's not the initial cost of acquiring the hardware. For about $1.50 an hour, you can get an FPGA in the cloud. Initial cost, very inexpensive. If you're using it for a long period, doing a lot of development, it can get expensive. But all of these things are going to improve. The costs will come down. The ease of the platform will come down. Third, which for some reason is numbered 1 again, it's probably an issue with the format translation of the slides, complexity and scale. And this is where transaction level Verilog comes into play, which we'll talk about more. But essentially, transaction level Verilog is obviously one of many new technologies that are coming along to introduce new design methodologies. Transaction level Verilog was built from the ground up for hardware modeling to address the challenges that we're facing today. Modularity and reuse, dealing with complexity and scale. So what's the impact of all these barriers breaking down? My expectation is actually that the impact of open source hardware on the hardware community will be even more impactful than open source software was on the software community. And the reason I say that is that hardware is fundamentally different in a few ways. Hardware, by its nature, as we talked about complexity and scale, is driven by very large corporations, right? Even more than the extent that software was driven by large corporations when open source software, gained momentum. So this enablement of individuals and startups is really going to shift from giant corporations to the smaller entity. You'll still have the large corporations developing ASICs that play into the data center, but now you've got the smaller guy enabled to utilize that data center hardware pool in new and creative ways. And also the open source hardware community has this broad base of open source ecosystem that's, the groundwork has been laid by open source software for us to just jump in. So I expect the transition will be relatively rapid for adoption of open source hardware mechanisms with all these factors converging together at roughly the same time in an industry that really hasn't changed much in the past 25 years. So it's a very exciting time to be in this industry. And all of this opportunity is coming just in time for the golden age of computing that David Patterson talked about in his keynote address, where all kinds of opportunity is opening up for creativity in computer architecture. Opportunities for custom hardware accelerators, custom hardware platforms, AI, machine learning, all these really exciting opportunities to go beyond von Neumann architecture that we've been doing for the past 30 years or so. Unfortunately, there is a fourth barrier, and it really hasn't come into play yet, but it will in a very significant way, and that's patents. I'm not a patent lawyer. I can't speak to all the intricacies here, but hardware patents are very different than software patents. It's much easier, not to say it's easy, but it's much easier to patent hardware, architectural concepts, etc. And as a result, there's a large minefield of patents out there that have to be navigated before you can implement anything significant. So when the open source ecosystem gets to the point where the open source contributors can start to contribute things that are interesting, large scale designs, you start to trip over patents more and more. And once you're into a realm of lawyers, you're beyond the realm of the open source community. So this is one that obviously I don't have a solution for, but I think it's important to call this out as a word of caution to the community. On a more personal note, I'm responsible, as Kunal said, for offering makerchip.com. This is an online platform, an online IDE for front-end circuit design. So this platform is targeting, breaking down all these barriers that I just mentioned to the open source community. So obviously access to tools, you just go to a URL and you're right there designing hardware. Access to the hardware. As I mentioned, cloud FPGAs are important, and the idea is to incorporate cloud FPGAs into this platform as well. It's not there yet. It'll be a while before it's in place, but the idea here is just to add that big red button. So after you've done your development of your design and debugged it, you push the big red button and off your design goes into the cloud, it gets compiled, it gets downloaded onto this cloud FPGA platform. Your model is running at full speed in the cloud, and you can interface with that design through your web browser. Complexity and scale. Obviously, transaction level Verilog is incorporated into this platform. It's incorporated not just as a language, but throughout the platform. The abstractions that are introduced by transaction level Verilog modeling permeate from development through the debug process and help to up-level the design process to make it easier to develop more substantial models. So let's jump into transaction level Verilog. So I'm going to lay the groundwork with a couple examples that illustrate some of the basic concepts behind transaction level modeling to set the stage for Akush and Ahmed's presentations. So I'm going to talk about timing abstraction and then a concept that builds on that called transaction level design. So I'll explain timing abstraction with this example. So here I'm implementing a circuit that computes a distance c using Pythagoras theorem as the square root of a squared plus b squared. And obviously that's a relatively deep computation. I'm not going to do all that in a single cycle, so I'm going to distribute that computation over 3 pipeline stages in this example, where I'm doing the squaring in the first stage, then the addition, then the square root. If we view this circuit in a timing abstract sense, we give ourselves the context of a pipeline. Here it's called calc. And within this pipeline, we drop the logic that's in the 3 stages. All right, so I've done nothing explicit with the flip-flops. I've just defined logic in their pipeline context. And from that description, the flops to get signals from one stage to another are implied. So looking now at the code level, you can see the transaction level Verilog code that has a direct correlation with the logic diagram. We're just saying in the code, I have a calc pipeline, and within 3 stages of its conceptually infinite pipeline, we have these logic expressions. So it's a very succinct expression of pipeline logic. The significance of this, part of the significance of this, not just that it's a compact representation, but representing the logic in this way, it now becomes very easy and very natural to retime the logic in a way that's safe. I can cut and paste expressions from this code from one pipeline stage to another pipeline stage, to move blocks of logic from one pipeline stage to another in a way that has no impact on the overall behavior of the system. Right, so this is very important for timing closure, which is a very significant part of the design process when you're designing at high frequencies. So free-flowing pipelines are a very natural part of computer architecture. They're a very fundamental and important part of it, but we don't always design all of our logic in free-flowing pipelines. So what if I want to apply back pressure to my logic? Right, so here I'm going to introduce a stall network into my pipeline to create the same logic within a stall pipeline. So the first thing I need to do for stall is provide the ability to hold on to values in these flip-flops. So when the stall condition arrives, I want to hold the values. I'm showing that as a recirculation through a mux. You could also hold the values by controlling the clock that feeds into the flip-flop, but I wanted to show things more explicitly here. And now that I've got the recirculation, I'll add in my stall signal to control the recirculation. So now I have a pipeline that's doing Pythagoras theorem that I can stall. If I take this logic as it is and just express this in transaction level Verilog, we now have to, so the back pressure, the recirculation of these values essentially breaks up the free-flowing pipelines, right? So each stage now in my stall pipeline has to be treated as its own mini pipeline. All right, so I've got 3 mini pipelines. I'm naming them stage 1, stage 2, stage 3. So these are pipeline names. And in that context, if I express my code in transaction level Verilog, it might look something like this. All right, so just to call out a couple things in this code. The retention of the values in stage 2, right? I'm taking in a squared and b squared and applying the stall condition to hold those values. So a squared and b squared, I'm applying the same logic to them to hold the value. So instead of expressing them independently, I'm going to use a more generic construct to express generically anything from stage 1. I want to be able to recirculate and feed into stage 2. Okay, so I'm using these any expressions to generically apply the recirculation to any logic within this pipeline coming from the stage 1 pipeline. And I've done the same thing for the stage 3 logic. Now, having done that, I can take these any expressions and pull them aside. So I've pulled them up top. So up top now, I have a generic expression that's describing a stall pipeline. Okay, it's generically saying my stall pipeline needs to recirculate values under the stall condition. Having represented that stall behavior in a generic way, now that stall logic has nothing to do with the particular transaction that's in the pipeline. The fact that we're doing Pythagoras theorem is irrelevant. This is just an expression of a stall pipeline behavior. So having made it generic, that generic behavior can now be part of a generic library. So I can create now a generic stall pipeline macro and utilize that stall pipeline macro to give myself the context now of a stall pipeline. So now we are to the point that we wanted to get to with this design, where we're just saying, I have a stall pipeline, and within the 3 stages of that stall pipeline, I have these logic expressions. They're the same logic expressions we had before with the non-back pressured stall pipeline. So, very easy to transform our design from a non-stall pipeline to a stall pipeline safely without introducing bugs related to the flow of the transaction through this pipeline. Okay, so that should set the stage about timing abstract modeling and transaction level modeling, which you'll see in both presentations from both Akash and Ahmed. I can take some questions, but hopefully most of the questions you can hold off on until they've had their chance to present. But if there are any quick questions now that you want to ask me, feel free to do so.
All right, thanks for the presentation. That was a very nice animation. So anyone has any query for him, or should we take it afterwards? Because the pipelining concept was very well explained. Just before you came, I explained them about the complex topics that needs to be understood in the whole world of chip designing, and you just explained, you just nailed one of them.
Great.
That's pretty nice. So anyone has any queries, or should we wait for Akash and Ahmed's presentation, and then we can have everything? All right, we'll hold on for the presentations. Next, we
right, thank you, guys.
Sorry.
Thank you.
Yeah. I'll just share my screen.
I sent you the presentation in PDF. Is it okay? Because
Sorry?
I sent you the presentation in PDF. Is it okay? Because
yeah, that should be fine. So
okay, thank you.
Yeah, so for everyone,
I remember Akash, you had 1 or 2 short animations. Those won't come through, but I think that's fine.
Yeah, we will see what happens with them.
All right, thanks, Steve. And let me introduce Akash Hadnagi. He's a master student at TU Delft. So Akash, you look very different in the photo and in reality. Yeah, he became involved in the WAP5 project through Google Summer of Code program this summer, and his interest includes heterogeneous and reconfigurable computing, FPGA, and hardware development. His topic will be formally verifying WAP5 and open source, which is an open source tail Verilog RISC-V core generator, just for something which Steve has introduced some time back. So, Akash, I'll just bring up your presentation and then I'll share the screen with you.
Okay.